let's start again at what does it actually do. So the first thing it does is it captures any linear change in relationship between features. So this is kind of the answer to the problems of univariate drift detection features that couldn't actually detect any kind of change in the correlations between features. The idea of multivariate drift detection is it actually can capture that. So it can capture the change in my second example that you saw with distribution 1 and distribution 2 switching places. It also captures changes in single feature distributions. So it kind of does the same thing as univariate drift detection models, but on a more global level. And of course, there's there's some drawbacks to that. And here I want to mention two, which is one, it requires at least 2 features to work because of the way the algorithm works that I'll explain in a minute. We will be doing dimensionality reduction at some point, and to reduce dimensionality, we need to have dimensions to reduce, which is not going to be a problem for almost any data set because you always work with multiple features in machine learning, apart from maybe some kind of time series analysis. And there is another issue is that because we're looking at multiple features at once, it's not as easily interpretable. But there's good news is that we can select a subset of features on our data to kind of try to narrow down where the change in data structure has actually happened. So we still get a bit of interpretability there. And at the end, we can come back to univariate drift detection to see whether the change in data structure is due to change in single feature distribution or correlations between features. So again, let's go over the input. So the first thing here is, and the only thing, fortunately, is we need to provide feature columns for our data reconstruction calculators, and we'll just provide the data for our features. We could also put in our model predictions, but that would mean that we're not really looking at only the covariate shift, but the entire distribution of model inputs and predictions at the same time, which is kind of a different thing. So we recommend that you take that you put only your features for multivariate drift detection. And the results, again, quite similar to before, when we have our reconstruction error, which is a measure of drift, and I will go into how we can obtain it and walk you through step by step of the algorithm that we use. Then again, you see confidence bands, which is basically how confident that our drift metric is within certain range. These are the ranges. And we have the threshold. And if the thresholds are again automatically determined based on the behavior of the metric on the reference data set. And if there is drift in your data, you will see that these thresholds will be exceeded in time. And then we have alerts, the small red diamonds that show you that something has gone wrong. Now, let's start building the intuition of what's going on in this algorithm. It looks a bit complex, but actually the premise is quite easy. So the main idea is that we're going to train or learn a compression decompression part. So let's say that we're going to train something like an autoencoder. And this autoencoder is going to learn the actual structure of the data in order to minimize the reconstruction loss, so the loss between the original data and the reconstructed data. And the key thing here is that we're going to rely on this compressor to correctly learn the structure of the data. And then we are going to measure the loss of this, let's say, autoencoder to measure how strongly the structure of the data has changed. So this is really the high-level intuition. So imagine here we have the compressing part of the autoencoder. We compress it to latent data, latent space, and we decompress it. And then what we're going to do is we're going to compare the original data with reconstructed data, like I do here. And for every place where they don't really align, we're going to be able to compute the reconstruction error. So now that you have the general idea that we're going to rely on this autoencoder to learn the structure of the data, and then we'll measure how good this autoencoder is on new data to see whether there is significant change in the data structure. Let's go into the actual step-by-step algorithm. So how do we train it? So first, we'll have to prepare the data. I'm gonna walk you through with how we train the algorithm in NumML, and we actually don't use autoencoders. We use the simplest possible thing, which is the PCA, because we don't need to capture the structure of the data fully. We just need to capture it well enough that if there's change in the data, the loss of the encoder-decoder changes. So it doesn't need to be low to start with. So we're going to prepare the data to make sure it can work with PCA. We're going to impute missing values. We're going to encode categorical features. And at the end, we're going to scale the data. Then we are going to train fit a PCA on our reference data. So it could be the test set, could be any part of your data, any period in the data for which you know everything is fine and there is no significant data drift and performance is satisfactory. So that what we're going to do is we're going to compress and decompress. So we're going to do transform and inverse transform of this reference data using our trained PCA, and this trained PCA again was trained on reference data. Then we're going to compute the distance between the original and the reconstructed points. So the points that gone through the compression, decompression using PCA. And we're just gonna do the simplest thing. We're gonna compute Euclidean distance between every pair of points. And then we're going to compute so-called reconstruction error, which means that we just take all the distances, all the Euclidean distances between those points, and we take the average of that. And for that, we know what is the general loss or the general reconstruction error of our PCA on reference data. It's not going to be 0 because it's lossy. We still need to reduce dimensionality. We're losing dimensions, which means we are losing information most likely. So we have some kind of reference reconstruction error. Then when we go into the drift detection mode, what we're going to do is we're going to look at our analysis data, so the data for which we want to figure out whether there is drift, and we're going to compress and decompress this analysis data using the trained PCA. And the important thing here is that we do not retrain the PCA. We use the PCA that we fitted on our reference data, and this PCA still remembers, and of course in quotes, what is the structure of our reference data. And then we're going to do the same thing. We're going to compute the distances between original and reconstructing points, and we're going to compute the reconstruction error again, so the average between those distances. And then we're going to compare this reconstruction error with the reconstruction error we got from the reference data. And in a moment, I'll show how it actually looks in a notebook. But the idea is that if this reconstruction error goes up, it means that the model has captured the structure of the data that is no longer suitable for compression and decompression. So the structure of the data has significantly changed in a way that the compression and decompression mechanism no longer works correctly. And again, kind of on the other hand, if the reconstruction error actually significantly goes down, then it means that the structure of the data again has changed in a way that the compression and decompression mechanism is better suited than it was on our reference data. So that again means that we have significant data drift or covariance shift.